Okay, I'm going to start the event tonight. I want to start by welcoming everybody to LPI, whether you are here with us physically in the room or whether you're with us virtually on the internet. Welcome to LPI and Cosmic Explorations. My name is Walter Kuiper. I'm the Associate Director here at LPI, and on behalf of Lisa Gaddis, Director, again, welcome. Our speaker tonight is Wong, who's a postdoctoral researcher at the Goddard Space Flight Center in suburban Maryland, just outside of Washington, D.C. He has the distinction of getting, the lucky distinction of being one of the people who gets to work on the science team, do operations of the James Webb Space Telescope, which has been producing fantastic images, and I'm sure equally fantastic science. I've been watching from the outside, and you have a cool job. Anyway, Ian will talk to us tonight on a revolution in solar system astronomy with James Webb Space Telescope, often just acronymed as JWST, and welcome.
Thank you. All right, let's get started. Pointer's not working. I'll just use my mouse. All right. Okay. So on Christmas morning in 2021, we had the best Christmas present. That is the picture-perfect launch of JWST from the jungles of French Guiana. And this marked the start of an exciting new chapter in space-based astronomy. And for the planetary science community in particular, this was a really long-awaited moment. Why is that? Well, there are a lot of limitations to ground-based observing. You have inclement weather, the existence of the sun, the daytime, as well as limitations due to the locations of your particular observatories. And most of all, it's the attenuation of incoming light due to Earth's atmosphere. So starting from the very early years of the space age, there was this push to send telescopes to space. And in fact, the first few attempts were to actually send spacecraft to rendezvous with these planetary bodies. So an example of that, probably exemplary pair of missions, was the Voyager 1 and 2 missions in the 80s. And those two missions brought back these spectacular images. And that really revolutionized space-based observations for planetary science, because we could now see at close range these spectacular spatial details that were unthinkable and still unattainable with Earth-based observations. So in the decades that followed, we have sent a veritable armada of spacecrafts all throughout the solar system. Not only have we revisited the gas giants, Jupiter and Saturn, but we have sent an array of instruments to the Moon and Mars, including rovers, as well as to a diverse sampling of asteroids and comets. So these spacecraft missions give us the really close field, detailed look at the surfaces and atmospheres. So one might ask, so why Webb? Why do we want to use this space telescope? Why won't we just send more spacecraft to these objects? Now, there's a few reasons for this. One is money and time. So these large spacecraft missions are these colossal endeavors, often one-shot missions that have very limited science yield due to the constraints of the trajectories. Also, there's limitations due to logistical considerations on the size and complexity of instruments that you can have on board spacecraft. So the best bet is to have space telescopes, large facilities dedicated to constant observations, where we can invest in developing the most advanced instrumentation. This is where James Webb really shines for solar system science. So perhaps the most famous space observatories, one of the great observatories is Hubble, which was launched in 1990. And it's been in operation for more than 32 years. And it has really revolutionized solar system science. It's revealed time variable behavior of clouds and surfaces of gas giants and their moons. It has revealed the surfaces of hundreds of comets and asteroids, something that you can't do with individual missions. And this is really unrivaled detail in both the breadth and the depth of science until now. So James Webb, launched in 2021, has a primary mirror that's almost 3 times the size of that on Hubble. In a hardware sense, it really just trumps Hubble in every conceivable way. Now, the mirror is this creative design consisting of 18 hexagonal gold-plated segments that are actually assembled in orbit. And this was just a revolutionary design that enables this sensitivity that was not achievable before. So another interesting aspect, and probably the most notable, is that Webb is an infrared instrument. Now here's an electromagnetic spectrum. Human eyes can see this very narrow band from 0.4 to 0.7 microns, called the visible wavelengths. And Hubble really was focused on those, with some excursions into the ultraviolet and near infrared. Meanwhile, James Webb extends our accessible range deep into the infrared, from about 0.6 microns all the way to about 30 microns. And this is a niche in the electromagnetic spectrum that hitherto has not been really sampled by any advanced instrumentation, and certainly not any instrumentation in space. And moreover, not only do we get imaging monochrome throughout this region, we have spectra. Now, spectra is when you take incoming light and break it apart into its constituent wavelengths. This gives you the maximum amount of information. You get the variation in brightness throughout this entire region. In essence, you're getting hundreds to thousands of individual colors from which you can glean a lot of detailed information about composition, surface properties, and other astrophysically interesting quantities. So why is the infrared important? And specifically, why is it important for solar system science? Now, probably the most important reason is that the infrared is a region rich in features. And what I mean by features are spectroscopic absorptions. So here in this plot on the upper left, don't want to read too much into it, but you're essentially seeing the fingerprints of various abundant ices that you find, for example, on the icy moons of the gas giants or in the Kuiper belt. So each of these species has a unique set of absorptions that, when detected, will not only let us know of its existence, but allow us to model its abundance, which tells us a lot about the formation and evolution of these objects. Now, another important reason for infrared studies is that it lets us peer deeper into atmospheres. So in the upper right here, you see a comparison of 2 different views of Jupiter. On the left is the visible, probably the most familiar view of Jupiter, where you see these high reflective clouds in the white bands. On the infrared side, you see a very different picture. You're actually seeing what was dark in the visible is now stands out as those bright orange regions. And what you're seeing is you're peering through the clouds into deeper layers and therefore warmer layers of the atmosphere. So by combining infrared observations at a range of wavelengths, we can actually derive the temperature as a function of pressure, which informs on a lot of fundamental processes like convection, wind speeds, composition, and other dynamical processes that drive this very dynamic surface of Jupiter. And last of all, there's also physical implications to infrared observations. Here on the bottom right, you see a deep infrared. This is 24 microns, infrared image of a comet near the nucleus. And those wavelengths allow us to see very, very close to the center and those details of the ejected dust and other features of the activity to driving this spectacular tails that we see in comets. And this is simply not possible at visible wavelengths. So Webb is armed with 4 spectacular instruments. In the near infrared, there are 3 instruments. At the bottom is NIRCam. This is the primary near infrared imager. So it allows us to obtain simultaneously images at 2 different wavelengths at very, very fine spatial scale. So this is going to be the workhorse for doing detailed spatial studies. The top is NIRSpec, which will be the powerhouse for spectroscopy in the near infrared. It involves several different modes covering continuous coverage from 1 to 5 microns. And this is a prime location for things like water ice, carbon dioxide, and other important species for compositional studies. Now, at longer wavelengths, we have a single instrument, the mid-infrared instrument, not a very creative name. but it takes the lead from 5 to 30 microns, measuring temperature and other important aspects of the mid-influence. Now, one specific observing mode that's very unique to James Webb's instrument is what's called integral field units. Now, if you imagine a prism, right, when you think of a spectrum, you think of a prism that's spreading light onto a single strand, a single row. Now, what an IFU does is it actually has essentially many, many different prisms, and it allows us to retain spatial information about the field of view. So the result is what we call a cube. It's a kind of a two-dimensional image at first glance. But for each of those individual pixels, we have a full spectrum, allowing us both compositional information and this spatial scale that we can then use to look at variations in location. So NIRSpec has an IFU. MIRI has a very similar observing mode called the medium resolution spectrograph, which offers the same sort of functionality for longer wavelengths. So when we hear the word infrared, most people think of heat, and therein lies one of the challenges in designing a very sensitive infrared instrument, because you need the instruments to be very cold in order to avoid the heat coming off from the telescope itself to swamp your detectors. So JWST has a very ingenious and very complicated solution to this problem. There are 5 very thin layers of a special material that dissipates heat, that is always blocking the main mirror from the sun. And this, that if you compare the temperature on the sun-facing side, it's very similar to a temperature on Earth. But on the instrument side, the side facing away from the sun, it's about -230 Celsius. And that's the necessary temperatures to avoid having significant contamination from the thermal emission of the telescope itself. So location of Webb is also very important. So unlike Hubble, which is in low Earth orbit, Webb is actually about 1 million miles away from Earth. It's in a special point called an L2 point, where the gravity is such that it is always in a line between the sun and the Earth. So it's always equidistant, roughly, from the Earth, but is actually separated very far from that. And that prevents interference from scattered light from the Earth and the Moon, and also allows us for continuous observations. So due to its special location, Webb is able to observe the entire solar system beyond Mars. This includes all the gas giants, as well as the main belt asteroids and the very distant Kuiper belt objects, which I'll get to at the very end of this talk. So in recognition of the very important advances that Webb will bring to solar system science, the Webb team has actually been awarded hundreds of hours of dedicated observing time during the first year to carry out a wide range of observations throughout the solar system. And here, just kind of a tabulated list of some of the targets and modes that will be used during the first year: all the gas giants, a number of their moons, Mars, Pluto, and other Kuiper belt objects. And the purpose of these is to showcase the capabilities of Webb in the realm of solar system science, demonstrate the technological capabilities of the instruments. All the modes are being represented here, and also produce some of the very pretty pictures that many of you have undoubtedly seen in the press from the first year of the mission. So for the rest of the talk, I'm going to take you on a whirlwind tour through some of the highlights from the first year so far of James Webb science observations. So starting off is probably one of my favorite observations to get involved in. This is the DART mission. So this is an artist's rendition of what happened here. And this is basically something from a sci-fi movie. What we did is we slammed this spacecraft, this multi-million-dollar spacecraft, into an asteroid in order to demonstrate whether we had the technological acumen to divert a potentially hazardous asteroid if one were to enter a collision course with Earth. And to say the least, it was a success. But in addition to this planetary defense motivation, the scientific community was very interested in this impact because all this ejecta allowed us to peer into the subsurface and really get at the physical nature of this really enigmatic near-Earth asteroid. So as part of this effort, JWST trained its NIRCam eye at this target before and after the impact. And you see this animation on the left here, this dramatic brightening and outgassing, expelling of material immediately after the impact. And these sort of span about 5 hours in time. And on the here's one of those frames on the right. And you can see not only this brightening, but also these kind of filaments of dust and rocks being spewed out far away from the object. Now, Webb was also joined by Hubble. This is the first big synergy from the first year of JWST between Hubble and Webb. And here you see kind of the different views. These are very different spatial scales, but you see very similar structure at similar times. And the DART team is eager to look at this data in detail. There's a lot of science to be gleaned from here. The grain sizes, the amount of energy that is lost from the impact, as well as interactions between the dust and solar irradiation. Moving on down to Mars, perhaps the most well-studied planet beside our own. So the red planet has been visited by dozens of orbiters and numerous rovers. And each time we learn something spectacular about the surface. There's strong evidence that suggests that sometime during the adolescent years of this planet, there was actually liquid water on its surface and had a very temperate climate, somewhat like our own. And evidence of this abounds from river valleys to gullies and delta formations. And there about Mars. One of the big ones is it's the presence of methane in its atmosphere. So Mars does have an atmosphere, but it's very tenuous. And the amount of methane that has been observed, particularly during the summer months on Mars. And this is sort of a mystery because methane is destroyed very rapidly by ultraviolet irradiation. So something must be producing methane. And we actually don't have a really good answer for this. And this is kind of the type of science that James will do. By observing the entire surface of Mars, we can map the abundance of methane over and over again. So we get both the spatial and the temporal dimension of this methane abundance. So Mars is quite hot when it comes to solar system objects. And it was actually quite challenging to design an observation that wouldn't saturate the detectors. But with some ingenuity and some data processing magic, we were able to pull it off. So this is actually the data that was released publicly from observations that were obtained on September 5th, 2022. So this is a NIRCam observations of Mars at 2 different wavelengths. On the left, you see the overlay of the fields of view over the representation of Mars surface. So at the top here, you have the observation at 2 microns. Now, this is primarily sensitive to reflected sunlight. So if you compare the optical photo in that image, you see kind of the same corresponding components. You have the dark volcanic basalts that are very dark in this image, as well as the brighter, dusty craters and basins on Mars surfaces. Now, the very different type of science is being probed at longer wavelengths. At 4.3 microns, you're primarily seeing emission, the heat coming off directly from Mars's surface. And this more or less tracks with the temperature of the surface. Sunlight is actually coming in from the bottom left. So the heat, the temperature decreases more or less monotonically as you get away from the sun, the regions of the most sunlight. But this is not always true. You can actually make out this large impact basin, Hellas Basin. And what we think is happening here is that because this basin is depressed relative to the surrounding topography, the light has to pass through more of the atmosphere. And 4.3 microns is the region where CO2 absorbs very strongly. So the reason why this is dark is likely because there's a lot more CO2 absorption going through the atmosphere before coming into JWST's detectors. So in addition to imaging, there was also spectroscopy. This is another publicly released data product from the Webb mission. And here you see a NIRSpec spectrum from the entire wavelength range from 1 to 5 microns. And you can see some of the major atmospheric components. CO2 dominates the atmosphere on Mars, about 95% of the abundance. But we also see some minor constituents like water and notably carbon monoxide. Carbon monoxide is very difficult to observe from the ground. In fact, this region really is opaque thanks to the atmosphere. So we really need a space-based instrument to look at this region of wavelength space. And James Webb is perfect for this type of observation. All right, so on to Jupiter. Jupiter is probably my favorite planet to look at. It's just such a spectacular atmosphere, all the swirls and vortices. So, you know, probably one of the most famous features is this great red spot. It's about, the length of it is about 3 Earth diameters, just to give you a sense of scale. Jupiter also has 95 known moons as of today. The 4 most famous ones, the Galilean satellites, are shown above. And all of them are different from each other. So in a sense, you can think of the Jupiter system as a solar system in miniature. You have a very large central body and a very diverse set of orbiting satellites. So one of the first images of a solar system object that the JWST released were these 2 images. So these are NIRCam images of Jupiter. And it's just absolutely spectacular. On the left, you can see a 2-color image, 2 near-infrared bands combined. If you look at Jupiter, you see dozens of bands, each corresponding to different jets of gas being transported by winds across the surface of the planet. Here, the great red spot shines very brightly, very reflective in wavelengths. Now, one of the most interesting features are at the northern and southern poles. These are actually aurorae, very similar to what we see in Earth. These are charged particles that are being accelerated and ionized by the very strong magnetosphere of Jupiter and impinging on the atmosphere at the poles. These are one of the most brilliant views of these to date. Now, looking away from the center object, we see these very tenuous ring structures. So Jupiter has 2 rings. You can really make out the more opaque inner ring. And within those rings are actually these tiny moonlets, 2 of them, which you can see annotated on that figure. And this just really shows the sensitivity of James Webb. To put this in perspective, the brightness of the rings is the ratio between Jupiter's and the ring's brightness is about a factor of 1 million. So in this single image, you're seeing a contrast of 1 million, and that's just spectacular. So I love this image. There's a lot to look at there. Now on the right is a slightly different version. This is actually a 3-color image. There's 3 NIRCam filters being combined here, and you can really see the vertical structure near the poles. In red here is where the aurora shines the brightest. You can see it's almost detached from the upper surface. And then you have a separate sort of green haze that's kind of covering the poles like a little cap. And those are actually just stratospheric hazes. And this is a separate phenomenon from the aurorae. So there's a lot of interesting vertical structure that can be teased out from these images. We also see these really bright red dots throughout the middle regions, the middle latitudes, sort of near the great red spot in particular. And these are upwellings, kind of storms, upwellings of ammonia that are being uplifted to high altitudes. And those show up at those little bright dots. So there's a lot of atmospheric dynamics that can be worked out in this image, and there are papers being written. A lot of people on the science team are very, very interested in this image. And by the way, this image was actually released for the purpose of science. This is actually primarily an outreach image, but nevertheless, James Webb delivers a lot of science from these 2 images. So for more on those. Now, I can't talk about Jupiter without talking about some of its moons. Perhaps the most interesting one, in my opinion, is Europa. So I like to call Europa the billiard ball cue, the cue ball of the solar system. It has a kind of a beige color, and it's indeed the smoothest solid object in the solar system. But notwithstanding its smoothness, if you look very carefully, in the upper left is a Galileo image of Europa, you see a lot of interesting roughness and structure. And all of this, these ridges, cracks, and modeled terrain suggests a very young surface, a surface that's constantly being replenished. So the leading consensus right now is that there is a large subsurface ocean with a depth of roughly 60 miles hidden under this crust of ice that's constantly being overturned. And this makes Europa one of the few proven reservoirs of liquid water outside of Earth. Now, there's probably some very complicated energetics going on. There's probably hydrothermal vents, a lot of energy exchange between the hotter core mantle and this ocean. And this brings up the possibility of habitability. And indeed, the Europa Kuiper mission, a planned mission that NASA will launch probably 2024, I believe, is to actually try to go to Europa and see what's going on in the subsurface. Now, one way of looking at the subsurface is if something is expelled outside to the surface. And there are some tentative detections of plumes, like geysers, emanating off of Europa's surface. There's some Hubble images have suggested that there are some plumes there. Now, these are not confirmed, but JWST is once again ideally suited to probe these. In the bottom left here, you see Europa overlaid by a hash pattern, and that shows the pixel scale of NIRSpec IFU in Europa's frame. So you can see that the surface is covered densely by these pixels. And with an IFU, you can extract spectra from each of these pixels. And what people will be looking for when these observations are analyzed are evidence for gas emission. So a sample spectra of some possible species that can be expelled from the interior are shown on the right, including carbon monoxide, carbon dioxide, and some very exotic species. So observations like this not only will give us information about the icy surface, but if plumes do in fact exist, this will give us a really good idea of what is going on in the ocean below the surface. All right, moving quickly now to Saturn. Saturn is another one of those photogenic planets. Here in the bottom is a backlit image from Cassini, the Cassini spacecraft, where you can see the very, very complicated architecture of the ring systems. There are more than 7 distinct ring bands that have been identified. Saturn also has its own menagerie of moons, about 83 known to date, including Titan, which is the second largest moon in the solar system, with a diameter of about 5,000 kilometers. So I want to talk about Titan for a bit because it's really interesting. So probably the image of Titan most people are familiar with is in the center on the left there. This is an optical image of Titan where it's enshrouded by this thick haze, hydrocarbon haze that kind of obscures the surface. But as mentioned before, infrared wavelengths are very powerful because it can peer deeper through atmospheres. And indeed, the Cassini spacecraft has looked at Titan quite a lot over about a 10-year period. And around this central image is a mosaic of different views of Titan's surface, composited from various Cassini images. And you can see a very, very complex surface. We have these dark orange regions around the middle, which are actually filled with sand dunes, very much like the Sahara Desert here on Earth. You have raised regions that are kind of white-purple in this image that are actually elevated and cut by gullies and all sorts of apparently hydrological features. So what's actually going on the surface can also be revealed from radar images. So this right image here is a radar composite from Cassini again. And this, if you were to show this, this almost looks like an Earth surface or like a topographical map of the Earth. And you see these lakes, these dark lakes. Now, this is not liquid water, right? The surface of Titan is at 94 Kelvin. So water is hard as a rock at those temperatures. What is actually flowing those lakes are ethane and methane. So this is a hydrocarbon dominated cycle. So Titan has a very dynamic atmosphere. It has the equivalent of the hydrological cycle, but instead is methane, methane rain flowing into methane rivers that flow into methane lakes. So this has been studied a lot over the past decade. So a recent image from James Webb published from the mission is this pair of, I call them marbles. They look like marbles, very iridescent and sparkly. These are 2 different views of NIRCam of Titan's surface. So on the left here is about 2.1 microns. So at this wavelength, the atmosphere is still pretty opaque, but not fully so. You actually make out clouds, 2 clouds in the northern part, as well as hazes near the south. The second is a composite of several different near-infrared wavelengths that are ideally suited for penetrating through the haze. And here you can see a lot of the surface detail popping out. And this is just a single image. You can see Belate, which is a region of sand dunes as well as Kraken Mare near the north, which is one of those methane ethane lakes. So this is just a taste for what James Webb will do in the Titan, in the Saturnian system. There are actually many more observations part of the set. This is just a fraction of what was obtained by James Webb. There's NIRSPEC spectroscopy, MIRI, imaging, and spectroscopy. So together, those will really paint a very detailed, unprecedentedly detailed image, picture of Titan. Enceladus, another an ocean world. This one has confirmed geysers. So on the upper right here is the image from Cassini showing multiple geysers shooting off liquid water and other materials into space. So Enceladus has a very interesting outgassing pattern. It appears to mostly be concentrated around the South Pole. So on the bottom left, the South Pole is actually sort of to the bottom left of that image. And you have these kind of band-like structures. They're called tiger stripes. And those are regions that are hotter and where the geysers are concentrated. So the idea is that it is through these gullies that the geysers are ejecting the materials. So like with Europa, there's going to be NIRSPEC spectroscopy and MIRI spectroscopy of Enceladus, which are currently in press. So keep an eye out for those in your favorite science publications in the coming months. All right, last stop on the planetary tour are the ice giants. The ice giants are very distinct from Jupiter and Saturn because they're much colder, and the distinctive blue color is actually from methane. Methane absorbs a lot of the reds and the oranges and the yellows, and what you're left with is this kind of nice blue color. To really understand the atmospheric dynamics, MIRI, the thermal wavelengths, are very helpful. And it just so happens that the fields of view of MIRI more or less hug these two objects very nicely. So in a single observation, we will be able to get almost the entire surfaces of these objects in one shot. So I had this, when I made this presentation yesterday, I had this plot up here. It was a very busy plot because I didn't know that there were Uranus observations, but that is changed as of this morning. Around 10 a.m. Eastern, this image was released by Webb. So on the left here is a wide field NIRCam image of the Uranian system. Uranus in the middle with its beautiful rings, almost face on, perfectly face on, and 6 of its largest moons, clearly seen in those little blue jewels. A close-up of Uranus reveals a very, very complex fact. 11 of the 14 no ring bands are visible in this image. Looking at the body itself, you see that it's not uniformly blue. There's these different regions. What actually is facing us is its northern pole. So Uranus, of course, has a very interesting axial tilt of almost 90 degrees, so that its north-south pole axis is about in the plane of the solar system. And you also see a very notable white patch at kind of the 10 o'clock region, and that's actually a storm. These are, again, sort of similar to what we saw on Jupiter, a storm of, in this case, methane rising and then condensing into ice crystals at the high altitudes. So Neptune, despite being the coldest, is actually the windiest of the planets. Some of the equatorial jets on Neptune can reach speeds of 1,000 miles per hour. It's also notable for its giant dark spot, which has changed in morphology over the decades that it's been monitored. Now, one of the mysteries of Neptune is its rings. So when Voyager visited in 1989, it saw a very rich ring structure, several different rings, concentric rings. And in the decades that have transpired since, it's been a challenge to re-observe these rings. Here on the right is in the Hubble image. You have the optical image of Neptune and then a masked image showing some of the structure around it. You have some of those moons and a few ring arcs. And this is kind of one of the best images from Hubble that we can get. So there was a lot of debate whether or not some of those rings, particularly the faint ones, were permanent, or rather sort of effervescent phenomena. Perhaps some ejected material from an impact on one of the small moons was temporarily creating a small ring. But James Webb settled that. So this is an image, this is released on September 21 of 2022. So the full image is on the right. This is, again, a NIRCam wide field image. You see this orb, the glowing orb of Neptune. And in the upper area is a saturated source, which is Triton, the largest moon of Neptune. Now, zooming in closer, we see 6 out of the 14 known moons, very close to the primary object, but also a number of these rings, 4 in fact. And 2 of these are those faint rings that were not seen since Voyager's flyby. This demonstrates the incredible sensitivity that Webb will bring for the study of the ice giants. Now, looking at Neptune itself, we again see some bright blotches. And these are once again storms that are moving along with those fast winds around the atmosphere. So as Webb continues its science mission, one interesting science avenue would be to revisit these ice giants periodically to see how those storms progress. All right, so leaving the giant planets, we move out to the Kuiper belt. The Kuiper belt is this broad region beyond the ice giants' orbits that contains a large number of leftover planetesimals. So these are sort of fossils from the era of planet formation, fossils that encode some of the most primitive characteristics of the building blocks of planets. Now, it's very difficult to observe these objects. They're very cold, they're very faint. But fortunately, we have 2 objects that we have very rich information about. This is all thanks to the New Horizons mission. So New Horizons flew by Pluto in 2015 and returned some truly spectacular views of its surface. This is one of my favorite pictures from that mission. This is you can almost imagine this is flying over the Tibetan plateau or something. You have these towering 10,000-foot mountains, but instead of rock, these are solid water ice mountains. You also see above the limb of Pluto the tenuous, hazy atmosphere that changes with the seasons. So the New Horizons missions revealed Pluto to be a highly dynamic object with a lot of very interesting surface features. Now, in contrast, the second flyby target, Arrokoth, is a much smaller, much more primitive object. It has this very interesting bilobate shape, appears to have formed as a binary that then touched sometime during its past. Now, Arrokoth is more representative of your typical garden variety KBO. It's extremely primitive. It probably has not encountered a lot of evolution, surface evolution, in the 4.5 billion years that had its formation. So New Horizons gave us kind of 2 end members. The largest KBO with very complicated geology, very complicated surface morphology, and a much more primitive object. So one of the highlights of James Webb is its ability to really lift the veil on the Kuiper belt. And this is thanks to its focus on the near infrared for one, and most importantly, its exquisite sensitivity. So during the first year of science, James Webb will actually observe the Pluto system several times. Now, I can't share any spectra or any details. It's still being written up, but I can kind of give you a taste of what the data is like. So on the left here, we see a New Horizons enhanced color image of both Pluto and its large binary companion Charon. And you can appreciate the gradients in color and surface morphologies across both of those surfaces. Now, in the upper right here, this is actually a compilation of dozens of ground-based spectra of Pluto in this case. This is actually over a decade of spectra combined together. And I can tell you that within a single hour of observation, Webb is able to deliver a spectrum of this quality. That's just really spectacular quantum leap in our abilities to efficiently characterize these objects. You see a surface with a lot of methane features, CH4 here. All these forests of lines are all methane features. You see some minor features due to carbon monoxide, as well as nitrogen. Now, the surface of Pluto is actually dominated by nitrogen, about 98% nitrogen ice. But spectroscopically, nitrogen is not particularly interesting. So methane really stands out the minor component of methane, really stands out in the spectrum. Now, when New Horizons flew by Pluto, the flyby lasted maybe a few hours. So all we had is this one hemisphere visible to the spacecraft. But we know from the ground and from Hubble that Pluto's surface is very inhomogeneous. Here in the bottom right, we have 3 different longitudinal views of Pluto's surfaces. You can see how there's a lot of variations in brightness across its surface. So what James will actually do during the first year is observe Pluto 4 different times, each time targeting 90 degrees offset from the previous observation. And together, it will stitch together in a spectroscopic picture of the entire surface. And I was able to share this. And this is actually JWST data. This is a NIRSpec image, well, NIRSpec cube image of both Pluto and Charon. You can see them nicely separated there on the detector. So what will happen is James will actually obtain a spectrum, continuous spectrum from 1 to 5 microns. So this actually exceeds the range of wavelengths that either or New Horizons observations were able to give us. And this extra wavelength range beyond what we can see here in the upper right plot contains a lot of very interesting features. And it is extra wavelength coverage that makes James Webb so powerful for studying these cold Kuiper belt objects. Occasionally, a Kuiper belt object is scattered inward, and at which point is called a centaur. Now, these objects cross the giant planet region, and they afford us the opportunity to study KBOs somewhat more up close, a little bit brighter, a little bit closer into Earth, and therefore brighter. Now, one of these objects is called Chiriclo, and there was a very unique opportunity during the first year of James Webb observations to carry out a very special type of observation. It's called an occultation. Occultation is when an object, a foreground object, in this case, Chiriclo, the centaur, passes over a background star, sort of like an eclipse. It blocks some fraction of the star's light. It allows us to get very detailed information about the spatial extent, information that is otherwise unattainable by any other means, save for a flyby mission. So what's really interesting about Chiriclo is that a previous stellar occultation revealed the presence of rings, namely 2 rings, concentric rings, very closely spaced together at some distance away from the main body. And this is actually a very surprising discovery because until then, it was thought that only giant planets have rings. Jupiter, Saturn, Uranus, and Neptune all have rings, but till then, no other small body was thought to be able to support rings. And this really turned the field on its head when it was discovered. Now, on October 18th, 2022, there was another opportunity to observe an occultation of Chiriclo. And this was actually a very special opportunity because the science scheduling was interrupted specifically for this very unique, once-in-a-lifetime alignment of JWST, Chiriclo, and this background star. And on the right here, the bottom right, is the light curve. This is the star's brightness as a function of time. And you see these 2 dips as the ring structure passed over the star. If you look very closely, each of those dips is actually 2 dips. And this confirms the previous claim that there are 2 concentric rings. This is a very spectacular, once a year sort of opportunity to use a James Webb in this way. Now, in addition to imaging, there was also NIRSpec spectroscopy of Chiriclo. And this is a spectrum that was released publicly alongside the occultation light curve. And here we see water ice. So unlike Pluto, which has a lot of methane and other features, these sort of smaller KBO and KBO analogs are mostly water ice. That's the primary absorbing species that we find on the surface. Now, water ice was detected previously from the ground, but not to this detail. And this spectrum actually allows us to constrain not only the presence of ice, of course, but also the specific phase of water ice, as well as information about its grain size. So this relatively short observation gave us a lot of information about its surface in a way that was previously unattainable from the ground or with Hubble. Right, so close to wrapping up here. So Pluto is the largest KBO, but there are a lot of other big guys out there. So here on the left here, I've shown 10 of the largest KBOs. And one thing immediately jumps out. Whereas Pluto, Eris, and Haumea, these are very bright objects with a lot of water ice on the surface or other highly reflective materials. A lot of the others are very dark. For example, Salacia has an albedo of about 4%. About only 4% of the light impinging the surface of Salacia gets reflected back. So about the darkness of charcoal, in fact. Another really interesting thing is that a lot of these objects have binary companions or small moonlets. And the fraction of KBOs that are thought to have satellites is very high, which tells us something about the formation and evolution of this population. So during the first year of observations, Webb will observe all 10 of these objects with NIRSpec and will provide us sort of a compositional map of the largest KBOs. Now, we can't talk about KBOs without talking about Triton. Triton, as I mentioned before, is a moon of Neptune, but it is due to its irregular orbit. We know that it's actually a captured KBO, so that would actually make it the biggest KBO. Yeah, so Triton. This is a Voyager 2. This image has a very interesting surface. It has kind of a cantaloupe, skin surface at the bottom there, transitioning to a lot more modeled surface towards the top. So Triton will also be observed at high resolution with the NIRSpec instrument, which will give us probably the highest quality KBO analog spectrum from the entire Cycle 1 program. So what can we learn by looking at KBOs? And I think I'm of the opinion that James Webb really shines in KBOs. I think the sensitivity is really what is necessary to bring a revolutionary new facet to our knowledge of KBOs. So KBOs have a lot of complex volatile ices and organics on their surfaces. Because they're cold, there are a lot of molecules that would otherwise be in the gas phase or on the ice in the solid phase. So by looking at the near-infrared spectrum, we can get kind of the inventory of volatile ices that initially formed with these objects, as well as study their variation across the population. So this is where comparative characterization comes into play. James Webb will observe all the largest KBOs, as well as smaller ones. The smaller ones, as I mentioned before, have undergone less evolution in their history and are more representative of the primordial nature of these objects. So throughout the first year, more than 80 KBOs will be observed. This is a huge treasure trove of data that will be coming down. This will allow us for the very first time to do spectroscopic and compositional mapping of the various objects throughout this region and really get at some of the fundamental aspects of their formation and evolution, which has far-reaching consequences for our broader understanding of the solar system. So I would like to end with a sort of exotic side note, but very relevant in recent years. So in 2017 and 2019, there were two very interesting objects that were detected and observed passing through our solar system. They were coming in at blistering speed, so fast that they were not bound to the sun. So these are called interstellar objects. And as the name suggests, these are objects that were ejected from alien solar systems, possibly tens of light years away, and just so happened to pass by ours on their lonely journey through the galaxy. And what's really interesting about them is that we have two objects, but they're so different from one another. The first one to be detected in 2017 has a fanciful name Oumuamua. And light curve studies from the ground revealed a really interesting shape. It appears to be extremely elongated. People call it a cigar shape. Either that or very flat, like a plate. And it's so extreme that it's very hard to find analogs of this shape anywhere in the solar system. So there are many, many theories as to what this could be, where it could have formed, and how it could have an unusual shape. The second object, 2I Borisov, was discovered in 2019, and it surprisingly displayed cometary activity during its closest approach. Much like a traditional comet that we see, like Halley's Comet, it had this beautiful tail emanating from a central nucleus. And there have been a lot of spectroscopic studies that have been published characterizing the volatile content. It appears that a lot of the elemental ratios are very different than those that we find in our own indigenous comets, so to speak, which may tell us something about the diversity in initial states of planetary systems throughout the universe. So I'll end on a sort of a forward-looking note. We're just about 8 months through the first year of Webb's science observations. And already there's been a deluge of new discoveries, not only in solar system science, but more broadly across the full gamut of subfields in astronomy. And this is really much just the beginning. Already, there have been some revolutionary new steps, new gains in our understandings of gas giants, of asteroids, of impacts, of KBOs, of comets. And it will only get better. And this treasure trove of data that will be available from the first year will continue being worked on by many more astronomers. Forward, this will become truly the world's observatory. I focused on most of these guaranteed time observations during this presentation, but going forward, this will transition to a fully competitive proposal process where any astronomer can apply for time for his or her special program. So I would like to thank once again LPI for inviting me to talk to you guys this evening, and I'll happily take some questions now. Thank you.
All right, if you have a question, just raise your hand. So one of the spectra that you were showing was about the methane on Mars. Where do they think that's coming from? Shouldn't it be like destroyed by ultraviolet radiation relatively rapidly?
Right. Yeah. So that's sort of the big mystery, right? So you know, if you had if a methane molecule were emitted somewhere, it would quickly rise to the top and be destroyed by UV irradiation. So the persistent presence of methane has to be supported by a consistent production through some means. There have been some various theories. One of the more fanciful ones, I think, is bacterial, I think, what is it, anaerobic respiration or something from bacteria producing methane. Somewhere in the subsurface, there's some microbes doing its thing and producing methane, similar to swamps on Earth and stuff like that. There are also some abiotic pathways. There's some interactions between the atmosphere and the rocky material on the surface, like olivine, that can produce methane as a byproduct. So there are a number of theories, some of them involving life, but certainly many that don't need life to support the consistent production of methane, but very much still an open question. So a lot remains to be seen with the methane.
Now, you mentioned that, you know, you're doing advanced robust science in like the first year of operations, but what happens after that year?
Well, so the data, so a lot of this data from that I talked about, I mentioned in this presentation, a lot of it's already public. So the international astronomical community can go and work on this data for their own purposes. You know, people have different specialities. They can look at different angles of the data. So this data this is not the end all be all of these images and data. So going forward, as models improve, as new data processing techniques improve, there will invariably be people who will revisit this data and glean extra science out of it. We saw this with Hubble. You know, a lot of people have been reprocessing Hubble data and getting a lot of exciting science out of it. So this data will live on and be useful for decades to come. And I actually neglected to mention that, there was a graphic that showed a kind of outdated graphic now, that said a mission length of 10 years. But what we actually think, thanks to the very precise orbital insertion, the very nice launch, that saved a lot of fuel, we think that 20 years is not unthinkable, perhaps even longer. So this is going to be an entire generation of new science being made available.
Clearly, the telescope is working extremely well, even better than we ever expected. However, I saw several other currents in the motors that were driving the filters. And I wonder if those problems are solved now, because you may very well have been the victim of one of these when I see the pictures you showed.
Can you repeat the question again about the filters?
Sure, there was another current in some of the motors that move the filters. Too much current, yes.
Ah, yes.
And I've seen that before.
Oh, yeah. So I don't know how much of this has actually been publicly shared. So there have been some roadblocks on the way. Now there's some growing pains. And with one of the instruments, I believe in MIRI, there were some issues with excess current being needed to change the gratings. So for several months, they actually paused MIRI observations. But that issue has been resolved. So MIRI is back online. All the science programs are back online with the full functionality. So, it's going well. So again, knock on wood that things don't break, as always.
Okay, so we have two questions from YouTube. So the first one is, are we sure that Oumuamua and Borisov were intergalactic objects and not displaced Oort cloud members?
That's a good question. So I'm not super familiar with the literature on that. There have been actually several different theories for non-interstellar origins for especially Oumuamua. I don't know, I just especially for Borisov. So certainly the trajectory that these objects were on as they were approaching the sun made it such that it was very difficult to find a dynamical reason for getting them on such high velocity orbits if they were scattered from the Oort cloud. Again, Oort cloud is one of those things that we don't actually never observe an object in the Oort cloud. It's sort of hypothesized it exists based on comets and the distribution of their orbits. But my understanding is that this has been looked at, and I think the consensus appears to be that it's very difficult to dynamically excite an Oort cloud object onto such a high velocity.
Okay, thank you. Then the next question is, do you know if JWST has any future plans to survey the main belt C-complex asteroids, those with volatile rich, or those objects that are volatile rich?
Yeah, certainly. I didn't talk about this due to time constraints, but during just within the guaranteed time observations, the first year, there are observation of Ceres, for example. Ceres, some of the biggest asteroids have been observed already during the first year. And there are also competitively approved proposals from other astronomers that are looking at other types, other subclasses of main belt asteroids. So it's perfectly capable of observing any asteroid in the main belt. So, if there's interest in any asteroid, propose away. It's up for the taking. So.
All right. Oh.
Time to time, I hear that Jupiter might have carbon monoxide excesses. I hadn't heard it in a couple of years, but just wonder if there's any follow-up on that, or if it could be monitored.
Unfortunately, I'm not really familiar with Jupiter side of things. It's not my research focus.
Pardon me when I saw it on the screen.
The carbon monoxide?
That would be in the spectra, yes.
I think you might be thinking of Mars. The spectrum I showed it was of Mars.
Well, in any case. But
there will be spectra of Jupiter.
The
but it's
situation
not.
with Jupiter at any rate.
Yeah. Unfortunately, I don't know too much about that. So definitely would be looking into that. Yeah.
Thanks.
In the renders you showed, why is the back of the JWST pink?
I think that's just a stylistic choice of the actual spacecraft, like folded up. I don't believe the back is pink. I don't know if it's a Mandela effect thing, but I don't think it's pink. But I could be wrong. Maybe it's pink. Yeah.
I just kind of wanted to know what's a day in the life of the James Webb Space Telescope? How does the day go?
The telescope itself?
Yeah.
So I think I didn't mention this in the talk, but one of the advantages of James Webb is its location. It's very far away from Earth and crucially not orbiting Earth. So that allows it to be observing the sky 24/7. It can be observing without interruptions. This is unlike Hubble. So Hubble is in low Earth orbit, has I think a 90-minute orbital period. So let's say you're observing a star near the ecliptic, half of your orbit is Earth is in the way. So James Webb doesn't have this problem. So its schedule is full, doesn't sleep. So how the scheduling works is actually quite complicated. So, and I don't have any hands-on experience with this, but you have all these approved programs for cycle 1, and different objects have different observability windows. James Webb always has to be facing so that its sun shield is protecting the instruments from the sun. So it can't turn to look towards the sun. So that places constraints on which objects can be observed at what time of the year. So there's a very complicated computer program that sorts all these observations by their observability, the number of instrument moves that required to set up the instrument. And there's also human input. So at Space Telescope Science Institute, there are actually schedule meetings that they sit down, kind of almost like an air traffic control. They kind of slot in different observations to try and optimize the efficiency of the observations. So just personally having some of my own observations scheduled, usually a week's worth of schedule is released about a week ahead of time. So about 7 days before when your observation happens, you get an email saying that your observation has been scheduled. And then you can look up this whole table of the sequence of observations. Yeah, but other than that, barring any instrumental issues, it just is it's like a computer script that's uploaded to the telescope and it just executes line by line all the different observations.
Along the same line, what fraction of the total observation time was spent for these marvelous solar system observations versus deep space observations? Obviously, it's designed more for deep space. And was it in year 1 extra heavy on solar observations, or does that current fraction of time for solar observations continue?
That's a great question. I don't have the exact number off the top of my head, but roughly only 5% or so, 5 to 10% of the time, a total on-sky time is dedicated to solar system science. There's another chunk of time that's devoted to exoplanets, which are planets outside the solar system. That's another big science focus area. But there's these huge extragalactic, high redshift galaxy programs that take up a lot of time, and that's a big chunk. So I think on the James Webb Space Telescope website, there's a pie chart. In some talks I've included it that shows the breakdown. And solar system, as cool as it is, it's a tiny sliver. Yeah, but nevertheless, from that time, just some great images. And I think going forward, I don't think there are any plans to dramatically change the breakdown. It depends on how many proposals are being received. So going forward, there's going to be less and less of these guaranteed time observations. So all the time will be competitively proposed for by astronomers. So it kind of depends on how many of each subfield worth of proposals are received. But I don't think that number is going to change dramatically from year to year. So I think going forward, the fraction will more or less stay the same.
Yeah, a basic question on your charts for spectroscopy. For someone who doesn't know much about that stuff, for things like methane and water along the wavelength line, there were like multiple spikes for one type of molecule. So how can you explain why you get multiple spikes?
Yeah. So so you can imagine, let's take water, for example. So water, the structure of water, you have oxygen, and then you have the two hydrogens. So there are many different modes that you can move these atoms around. You can twist the arms. You can stretch one while contracting the other. So there's all these different vibrational rotational modes, we call them. So each of those has sort of a central wavelength at which it's triggered. So the more complicated the molecule is, the more asymmetric a molecule is, the more of these individual modes that you can excite this molecule in. So each of those little lines corresponds to a particular way of bending, stretching, or rotating this molecule.
I have two questions. First, kind of related to the previous one, how long on average do these images take to collect or the spectrum take to collect?
Yeah, so it's mostly dependent on the brightness of the object. So for Mars, it's super bright. If you, the way that we count the exposure time is by groups and frames. I don't want to get into the details, but the Mars observations were basically the minimum amount of exposure time you could take, which is about 10 seconds, I think, or even less. So that's how long the shutter is open, so to speak. For some of the fainter objects, like the smaller KBOs, we're looking at hours of continuous exposure. So you have many orders of magnitude of variation depending on the brightness. So it really depends. Also, if you are using imaging, is typically faster because you're not splitting the light into the component wavelengths. You're just gathering it. Whatever falls into the filter goes onto the detector. So imaging observations are much faster than spectroscopic observations. That's another consideration.
And second question on the time-lapse video of the DART impact. Did you say those are 5-hour frames or in between?
So between each of the consecutive frames, about 20 minutes. Yeah, there's a few frames that were skipped. But yeah, from end to end is about 4 to 5 hours.
Okay. Do you know what's driving that kind of like continuous ejection of what looked like material, or is that?
And that's something that people are working on, trying to model all those jets. And there's not just one. If you think about, usually when you think about, throwing a wad of ink at the wall, right? You just one big kind of splat. But it really does look like there are these individual jets that are coming out from the impact site. And as those jets are moving away from the central body, they're changing shape in some interesting ways. So I don't know, it ultimately has something to do with the surface properties, how rough the surface is, how many little pores there are, if it's a very porous surface versus a very solid, dense surface. It all affects the way it reacts to this impact. So there's a lot of teams working on very complex simulations, trying to recreate those strands that coming off the object. So yeah.
Yeah, I think one more here.
And all the pictures I see of the James Webb Space Telescope, the telescope is pointed almost perpendicular. How is that just an artistic rendition, or how limited is the range of motion of the telescope relative to the sun shield?
Yeah, it's pretty limited. So there's these reaction wheels that control the pitch and the yaw and everything about the orientation of the entire telescope. And it's mostly moving as a unit. And that places limits on where you're looking in the sky. There's like a certain number of degrees around the central pointing that you can, the leeway that you can use to move that.
Okay, so we thank our speaker one more time. Thanks for joining us this evening. Our next presentation in our series will be on June 8th. LPI's Dr. David Kring is going to talk to us about the geology of the lunar South Pole. and how that relates to Artemis 3 potential landing sites. So we'll see you then. We got a reception outside.